All right, so we're going to look at the first half of section 9.1, which is conics, parametric equations, and polar coordinates. That's all of chapter 9. Today we're just going to be looking at conics, specifically parabolas in terms of conics. So we're actually going to skip over this first part of vocab just because you could easily go back and fill in this vocab words just from looking in the book, so I'll let you do that on your own. If I come back here, it says a conic section, or conic, as you can call it, is the intersection of a plane and a double-naped cone. It says name the four basic conic sections: circle, parabola, ellipse, and hyperbola. Sorry, that's supposed to be an E, kind of got cut off. That's an ellipse and hyperbola. If you want to look at the pictures of them, you can open up your book. Let me just figure out what page it's on really quick. It's section 9.1. So open up your book to page 637, and you can see a picture that shows the four conic sections. So circle, parabola, ellipse, and hyperbola. So, if we go on to this page, it says, in the formation of the four basic cones, the intersecting plane does not pass through the vertex of the cone. So again, if you look at page 637, you'll see that those first four don't pass through the vertex of the two cones where they meet. When the plane does pass through the vertex, the resulting figure is called a degenerate conic. And those are the next three examples. So figure 9.2 on page 637. Those three pictures are pictures of degenerate conics. And they create points, lines, and two intersecting lines when you get a degenerate conic. We won't be looking at those, but that is what they are called if you see them. In this section, each conic is defined as a locus. A locus is a collection, so you can write that down if you want to. A collection of points satisfying a certain geometric property. So it's the collection of points satisfying a certain geometric property. For example, a circle is a collection of all the points x, y that are equidistant from a fixed point. So they're all the same distance from some point hk. And this is the formula for the equation of a circle, which hopefully you know already. X minus h squared plus y minus k squared equals r squared. And then parabola. A parabola, which is the one we're going to look at today, is the set of all points x, y that are equidistant, again, equal distances, from a fixed line, which is the directrix, and a fixed point, which is the focus, and that's not on the line. So if you think of a parabola that looks like this, there's some line down here called the directrix. Oops. And there's a point in here called the focus. And all the points on the line, all the points on the parabola, are equidistant from that line and the point, not on the line. So for example, this point here is equidistant to this point here. This point here is equidistant to this point here, so on and so forth. So you get kind of the point from what that is. All right. I guess I can erase all that. All right. The midpoint. The midpoint between the focus and the directrix is the vertex of the parabola, and the line passing through the focus and the vertex is called the axis. So that's the line going straight down the middle that makes it symmetrical. The standard form of the equation of a parabola with a vertical axis having a vertex at h, k and a directrix at y equals k minus p is that equation. And then you can also write the standard form of the equation with a horizontal axis. So it just depends if it's facing up or down or left or right. And the focus lies on the axis p units from the vertex. So the coordinates of the focus are h, k plus p, or h, k, h plus p for a horizontal axis. All right, we're going to skip this question really quick and move on to this piece. The last piece for today's notes here before we move on to some examples is a focal chord. A focal chord is a line segment that passes through the focus of the parabola and has endpoints on the parabola. So for example, if I look at this parabola, and this is the focus here, a focal chord is any line that passes through that point, like this. That third line I just drew, the one that goes straight across, it's a specific kind of focal chord. It's perpendicular to the axis. So remember that this is the axis of the parabola, the line that makes it symmetrical. So that last focal chord I drew, this one here, is actually perpendicular to the axis, so therefore it's called the latus rectum. And the reflective property of a parabola makes it so that it has two properties. Number one, the line passing through P and the focus make equal angles with each other, and the line passing through P parallel to the axis of the parabola is also makes equal angles to each other. All right, let's look at some examples. Do it on whiteboard paper. Perfect. All right, so this is example number 1. It says to find the focus of this parabola, y equals -1/2 x squared minus x plus 1. So the first thing we can do is we want to complete the square to make it look like the standard form of the equation of a parabola. So I can factor out a 1/2 first. So I have y equals, I'm actually going to rearrange the terms as well. So I'm going to factor out a 1/2, and then I'm going to put the last term first, so that'll be 1. I'm going to put the middle term second, so that'll be minus 2x, and then the last term will go last, minus x squared. Perfect, just so that I don't have to have that negative at the beginning. Now if I multiply the 1/2 over to the other side, I get 2y equals, and I'm only going to group, if I write this like this, I get 1 minus 2x minus x squared. And I'm actually going to group together things that are important to me. So I'm going to group these two together, and I'm going to factor out that negative. So I get 2y equals 1 minus 2x plus x squared. And now I'm setting myself up to complete the square. So in order to complete the square, I'm going to add 1 inside of the parentheses, because it's x squared plus 2x. Obviously, to complete the square, you divide 2 by 2 and square it. So 2 divided by 2 is 1, squared is 1. So I'm going to add 1 inside the parentheses, but since it has the negative in front, it's actually subtracting 1. And then I'm going to add 1 outside the parentheses. So I have 2y equals 1 plus 1 minus 1 plus 2x plus x squared, which simplifies to 2y equals 2 minus, that factors to 1 plus x quantity squared. So we have 1 plus x quantity squared. I don't want that 2 on this side of the equation, so I'm going to move it over to the other side. So I get 2y minus 2 equals negative. I'll just rearrange this to say x plus 1 because I like that better. And then if I divide by a negative, I get negative 2y plus 2 equals x plus 1 quantity squared. And then last but not least, I can factor out a negative 2. So I have negative 2 times y minus 1 equals x plus 1 quantity squared. So this looks a lot like my standard form, standard equation of a parabola, which is x minus h squared equals 4p times y minus k, where p is actually equal to the point, I'm blanking on the name, but anyway, this is my p that I'm looking at. So this is in the standard form, this is 4p equals negative 2. So you can conclude that h is equal to negative 1, because of right here. The formula says x minus h, so minus would obviously make that a negative 1. K is equal to 1, and 4p is equal to negative 2, which means that p is equal to negative 2 over 4, which is negative 1/2. And the directions say to find the focus. So the focus we wrote down is at the point h, comma, k plus p. So that would be at negative 1, comma, 1 plus negative 1/2, which is at negative 1, comma, 1/2. And that is the coordinates of the focus. And if you look at the picture in your book on page 638, it shows you, I'll put a picture of it right here, shows you the parabola, and it shows you that we put the focus in the correct place at negative 1, 1/2. So that's the focus of the parabola. All right, good. Let's move on to example 2. All right, so this is example number 2 on page 639. It says find the length of the lattice rectum of x squared equals 4py, then find the length of the intercepted arc. So the fact that y is not in parentheses with a number means that it's centered on the y-axis, because y is obviously not shifted anywhere. And it's facing up because it's positive. So we know that it's going to look something like this. All right, and x actually doesn't have anything being added to it either, so it's not shifted anywhere in the x direction or the y direction. So we know that the vertex is at 0, 0. It's going to have a focus right here somewhere at 0, p. And I know that over here I'm going to have a point where if y equals p, then that means that x must equal 2p, comma p. And over here I'm going to have a point at negative 2p, comma p. And again, here's the reasons you know that. So you know that 0p is there because that's the focus. If you actually plug in p for y into the equation, you get x squared equals 4 times p, which is 4p squared. And if you take the square root of that, you get that x equals plus or minus 2p. So that's how I got the plus or minus 2p for the x coordinates. All right, good. So if you look at the length of this line, the length of the lattice rectum, it's 2p one way and 2p the other way. So if you add 2p plus 2p, you get 4p. So the length of the lattice rectum is 4p. So that's the first half. It said to find the length of the lattice rectum, and we concluded that it was 4p. Now we need to find the length of the intercepted arc. So that's this piece here that they're looking at. They want to know how long is that intercepted arc, and we're going to have to use the arc length formula that we learned back in the last chapter we were looking at in chapter 6. So if I can erase some of this stuff, the formula for arc length is S equals the integral of the square root, or from negative 2p to 2p, of the square root of 1 plus y prime squared dx. So, because this is an even function, the negative 2p thing, we can use the rule that it just doubles up from 0 to 2p. You can use the area and just double it. So from 0 to 2p of the square root of 1 plus, well, y prime. If I solve this equation for y, I get y equals x squared over 4p. So therefore, y prime equals 1 over 4p, because that's just a constant, times the derivative of x squared, which is 2x. So this equals x over 2p. So this is x over 2p quantity squared dx. So let's see, I can do 2 times integral. I'm going to stop writing from 0 to 2p for a little bit if that's okay with you. If I square that, I get 1 plus x squared over 4p squared dx. And if I want to combine like terms, I get 2 times the integral of 4p over 4p plus x squared over 4p squared. Sorry, that's supposed to be a p squared dx. So I can actually pull out that 1 over 4p squared from the radical. So I get 2 times the integral of 1 over 2p, because when I pull out that 1 over 4p squared, that's what it turns into, times the square root of 4p squared plus x squared dx. And I can pull that outside of the integral, so the 2's cancel. I get 1 over p times the integral of the square root of 4p squared plus x squared dx. Now hopefully that looks familiar, because that's the integral of the square root of a squared plus b squared, or sorry, plus u squared du. So hopefully that looks familiar to you, because that's one of our integration rules. So when I integrate it, I get 1 over p, excuse me, and then the integral of, where a, by the way, a is equal to 2p, and x is equal to u, or u is equal to x, I should say. So when I integrate it, excuse me, I get x over 2 times the square root of 4p squared plus x squared plus 4p squared ln of the absolute value of x plus the square root of 4p squared plus x squared. And that's all from 0 to 2p. So again, that integral, check that integral to make sure that it makes sense to you, how we got the square root of a squared plus u squared, the integral of that to be this. So, excuse me, when I plug in the 2p and I plug in the 0, if I can erase some of this stuff up here. All right, if I plug in those, this simplifies to 1 over 2p times 2p square root of 8p squared plus 4p squared ln of 2p, plus square root of 8p squared minus 4p squared ln of 2p. I know it's a lot. The fact that they don't have a p kind of makes it weird because you can't actually plug in anything for that, but sometimes you just have to make it generic. So we have 2p, and then all of that simplifies to the square root of 2 plus ln of 1 plus the square root of 2. And if you put that in a calculator, you get 4.59p. Whew. And that's how long the arc is, depending on what p would be. All right, perfect. So that's it for our notes for today. I'll put some homework on the board for you tomorrow.